Todd Spurgeon from the DREAMS Lab, or Design for Research and Education in Additive Manufacturing Systems through Virginia Tech. We basically do additive manufacturing, or what most people consider 3D printing research. So we just look at designing structures with with different functionalities. Now, this functionality could be just from designing a geometry that is weight optimized or has certain structures to it. So, for instance, we modeled the stresses on a beam, and we took away material where it was not being used until we got a very much weight optimized structure. And we also printed this cell structure, which reduces the weight, as well as it allows you to thread components and mount components onto this rack. You can design contours just so that that you get the part that you're looking, or you get something that exactly fits a piece that you're looking into, and you can design integrated assemblies with this. You can also embed other materials and other together to get different functionality. So you can say put a soft material where you need some give in the structure, or put a hard material where you really want it to be very stiff. So we can look at functionally grading materials, as well as embedding actuation or some acoustic metamaterials to be able to actuate a different structure, or actuate a structure sort of like an aileron, just through without having to integrate, say, servos or other actuators into the device. So we do a lot of research. Another bit of our research and our challenge with the DREAMS Lab is education. So training the workforce and teaching our students when is there a good application for additive manufacturing, as well as when there is not a good application for additive manufacturing. So some place where you needed a million of a certain structure, unless that structure really needed to be designed with additive manufacturing in mind, such as it needed a certain contour, a certain geometry, a certain weight, then it probably would be more likely, or you probably would more want to put that or make that with injection molding. If you needed a customized structure, or something that is tailored specifically to the application or to the user, additive manufacturing makes a lot of sense. If you needed to build things in certain layer-wise structures, or you needed to change things as you needed, or reduce your supply chain. So instead of ordering thousands upon thousands of parts, you have just the material, and you have a library or a catalog of parts that you print as you need them, or as they need to be replaced. Or you can customize brackets for other devices. But really, the applications for additive manufacturing are endless. Did you know that the Invisalign braces the molds for those are actually created with additive manufacturing, then they're vacuum formed over, just because it allows people to create that customization that they need. Defense applications. So say if you needed a multi-rotor to do observation, you could mount a camera on one of these systems and design something that holds this in place as you need. For defense, we've had users or people in the field where they've taken, or they see something on their system. So like there's a user, a soldier, that had a flashlight, and it kept turning on because the button wasn't protected enough, and it was draining the battery. So he could possibly be in a combat scenario, need that flashlight and not be there for him. So he designed in the field and printed a cover for that flashlight, and it stopped. And it was just a small, quick part, low volume, but it was just what he needed for his situation. Instead of having to go back and purchase another flashlight with a better solution, he was able to adapt and change things with a minimal time, so that he was used to create that solution, as well as the minimal time to implement it and test it. If you see that there's an issue with this vehicle, the user or the person on the ground could be like, well, I would really like it if this camera was at a different angle. So you could change the angle of the bracket in the CAD model, and the next one that comes off the assembly line, per se, or out of the printer, would have that change adapted to it. So it allows you to adopt these different missions. This could hold a Geiger counter for some sort of scenario where there's a radioactive spill, or some sort of insurgency, where a surgeon's got a hold of a radioactive device or radioactive weapon, and you could use this to survey a region to sort of try and spot it or find it. Or in the cases of a chemical spill, you could put these sensors, you could mount these sensors and design something custom for those devices, instead of having to duct tape them frantically onto another system, or having to risk a much more expensive device that would say, like, one of these drones could be $10,000 to make, or one of the custom or one of the currently existing drones is like $10,000 to produce and to field. So that's a big investment. One of these systems is about $100 to $200. So this is effectively disposable as far as the military or defense could be concerned. So it really does just, you have to look at what applications you're doing and when additive makes sense. That's just the training on that, a little bit of, or the training and education on teaching people and teaching users how to analyze what their need is and when this should be used is another big challenge for the Dreams, or that the Dreams Lab looks to tackle. I would recommend searching Dreams Lab, or DREAMS Lab at Virginia Tech.